Thank you, Søren. Are you there, Torvald?
I'm here, and thank you for giving me the possibility to talk to all you today. My name is Torvald Petersen. I'm the CEO of Listen Energy, and we are have been in this business with the energy production from biogas in 30 years now. What I will talk about today is why the CHPs, combined heat and power gas engines, are very popular in this business. So for wastewater treatment plants, the teaser is that you can become energy neutral and produce your own energy, and at the same time plant a green footprint on your plant. We are working in this sector for wastewater, food waste, also biogas plant with manure and organic industrial waste. So what we take care of is the gas from it comes out of the digesters, as you saw an example from Flemming Møller from Aarhus Water. We take the gas there, and then we are in this line where we start with the gas treatment. We treat the gas after coming out of the digester with different kind of technology. Then we produce CHPs from down to 63 kilowatt up to 2 megawatt. In most cases for wastewater treatment plants, it's about 300 to 500 in the bigger plants, up to 1.5 megawatt. And for biogas plants, it's a little bit higher, from 1 megawatt to 3 megawatt. So we are in this can supply equipment in this range. Can you give me the next slide, please? So the CHPs, why CHPs? The CHP had the advantage that it produces heat and electricity at the same time. So for wastewater treatment plants, and in many cases biogas plants, the highest efficient utilization of biogas is to have this combined production. So the CHP take the fuel you produce on the wastewater treatment plant or the biogas plant and convert it to heat and electricity. And for wastewater treatment plants, the advantage is that you use a lot of heat for the digesters and the building heating, and also a lot of electricity for pumping and aeration and so on. So looking into a circular economy, you produce the gas and then you convert it and use it at the same time, actually. Then it's also the advantage is decentralized production. We have an example, for example, in Glimbad, the first one we produced, that we was not allowed to export the electricity. We had to run according to the consumption of the plant. But today they are allowed to do that and actually ask for it by the electricity company, because they find out that they had to spend money on expanding the grid system, because the electricity consumption in the area was rising. So then they had the local production at that time, and that gave them the possibility to produce electricity nearby. So that was also an advantage here. Reduction of CO2 for using the biogas is also a question here to plan the greener footprint. And then it's finally it's a local renewable energy source for the community. So as we see, that's the way the most utilities want to go these days. Please give me the next slide. So looking into the CHP system, we have a very high efficiency, as also Fleming expressed in his presentation, that we can have a very high production and utilization of the biogas, and that's really the advantage of the CHP. Converted to the traditional system with about the highest 50% efficiency, we have up to 95% efficiency on a CHP system. I will address this because one of the most critical part when you are going into install energy production from your plants is to size the CHP system, or the size of the gas engine is really critical, because the highest efficiency is reached when you have the CHP system in a range of 75% to 100% of the capacity of the CHP compared to your biogas production. So that's where the high efficiency comes from. If you, for example, specify a CHP which has the double capacity of what you have, you can produce of biogas, then you will have a lower efficiency. So it is really important to look into this system. Another thing for the efficiency is not only the figures for conversion, but it's also to be sure that the gas is clean and can be used as fuel for CHP, so you have a high uptime. Because you want to run this system 24/7 all day year, because your plants produce biogas in these all this time. So access to service is also a key. So it is important to have a quick access to service if needed and parts, so you can reach this uptime. We normally reach about 93 to 95% of uptime too, and so therefore we are very on top of provide service and parts to the clients, because that is also very important. Yes, that's it. Next one. So I will just give you an example, because the two learning points for me is to size the CHP right and get the right gas cleaning system in front of it, so you can be sure that the fuel is beneficial, and get access to the service. That is the three learning points, which is really important when you choose CHPs. Here I will give you an example also. Fleming told about our containerized system, which is quite a plug-and-play system. We supplied such a one, which was started up here 3 weeks ago in the Hermitage wastewater treatment and food waste facilities, and they raised the efficiency of utilization of the gas with 60% after they have installed this new system. But that is rather quick. It's rather quick to install at site, because it's a kind of a plug and play. So there is small connections to be done to get the heat into your facility and get electricity out of this. So it is one of an example for application for food waste. The next slide, please. Another case is Downwards Grow. You have just seen Landia express that they have supplied the gas mixing system to this plant. And when we talked to them first time, there was the aim to be energy neutrality, have energy neutrality at the plant. And they have reached that now. And they have also further plans. So we supply within 2-3 weeks the next CHP to them, and this runs with a 40% electrical efficiency and has a payback, have been the first one we supplied to them, had payback time of 3.5 years. So that's also possible to get energy neutrality in the US plants. So I will just say thank you, and I'm also later on ready for questions when you might have. Thank you very much.
Amon gas?
Yes,
Super.
there you are.
Scene is yours, Alexander.
All right, thank you. So I'm here to talk about the biogas upgrading solution, where we purify the gas instead. Next slide, please. So first, a bit of introduction to Gas. We're a small engineering company that specializes in environmental systems, that is, in this case, scrubbers and ammonia separation and condensation and carbon filters, and of course, biogas upgrading, as we'll be talking about today. We are located in Copenhagen, Denmark, and we have just around 40 plants around the world, mostly in Northern Europe. And my name is Alexander, and as a background, I'm a global business engineer from the Technical University of Denmark, and I've been in Gas since 2016, where I started out as a project engineer and now moved up. All right, so this is the gas upgrading system. We use Airmine to upgrade, which means we run with a pressureless system. That means that the entire upgrading process is, where you can see it says gas upgrading. Here we separate the CO2 and the H2S as well. And then afterwards, we do all the gas conditioning, the compression, the gas drying, and the analysis. Because of this, the pressureless system, we have a relatively low electrical power consumption because we don't need to compress the CO2. And because it's a chemical reaction, the methane slip is also very, very low. So the CO2 comes out quite pure, and it can be used for other applications if carbon capturing, for instance, could be of interest. Next slide, please. So this is the process. I think, is there a reaction if you press again on the slide? Yes, all right. So what happens is, a bit back, thank you. So what happens is, in the absorb column, we take in the raw biogas, and then we wash it with a organic solvent called Airmine, a water Airmine solution. And the reaction is more or less like a soda streamer. So the CO2 will react with the water and make carbonic acid, just like in any soda. And the Airmine will then react with the carbonic acid and absorb that into the Airmine water solvent. And if you press again, then we transfer the now CO2 filled Airmine water into the desorber column, where we apply heat. And then we boil out the CO2 and H2S and all that. So because of that, we of course need heat to strip out the CO2, but that heat can be recovered and used in the upgrading process. After this, we will need to clean out the H2S as well, which biogas cleaning can tell more about their biological desulfurization process. So that means the entire upgrading process is actually only the absorber column. And all the rest of the system you can see here, that's just to regenerate and reuse the Airmine, so there's no Airmine consumption. Next slide, please. Oh yeah, and that's the return heat that comes again at two temperatures, a medium and a high temperature. I can see it's the wrong degree, I'm sorry about that, but around 85, 90 degrees Celsius and 50 to 60 degrees Celsius. And we can have around 70, 80%, up to 90% in some cases of heat recovered. So if you press again, yeah, thank you. And here we have an example of it. So the point when we look at this is to integrate the upgrading system into the anaerobic digestion, so into the biogas production. So for this case, we have a boiler that supplies heat to the upgrading process, and a bit heat to the biogas production process as well. So what we do is we take the medium temperature and direct that into the mixer, and we heat up the material, the solid and the liquid fraction in the mixer. And then we have the high temperature, which we apply to the reactor tanks directly, and to run a thermophilic biogas production in the reactor tanks. So for this specific case, we need a bit of heat from the boiler directly to the reactor tanks as well. But if you go to the next slide, we have another example. So for this case, what we do is we take the medium temperature and we preheat the liquid fraction instead, because it's easier to heat the liquid fraction. So already before it enters the mixer, it has a good temperature, and we get almost the correct temperature in the mixer actually. And then we apply again the high temperature directly into the reactor tanks. And for this case, as you can see, we have 3 kilowatts. So a very, very small supply from the boiler directly, meaning that actually the majority of the heat is supplied directly to the biogas upgrading plant. And then the biogas upgrading plant will supply the needed heat to the anaerobic digestion. Next slide, please. So this is actually the case from the picture before. This is Madsen Bioenergy in Skive in Denmark. And in the building, you can see it has a biomass heat exchanger. And that's where the liquid fraction is heated. And all the heat supplied to the plant is from a biomass boiler, which supplies heat into the upgrading plant, which is in the small blue circle. You can see the 2 columns there. And that supplies enough heat to heat up all of the biogas production. And as it's stated here, there's a 90% heat recovery for this plant, which means the upgrading process actually only used 10% heat, because the rest of the heat would be used in the biogas production anyway. Next slide, please. And here's another example. So here we actually have, they use a mesophilic process, biogas production, so they don't need a lot of heat. However, they do have household waste. So they need to heat that up for the pasteurization process. Further, the system is further integrated so that you can actually see Biogas Clean's H2S removal system there. And after that, it goes into a integrated flue system that also takes care of the smell reduction from the receiving station. And the entire system is run in the small building in the bottom of the picture as a complete integrated control system with the entire biogas production, the upgrading plant, and all that necessary can be run from there. All right, next slide, please. I can see I have to hurry up a bit. So we have some different uses for the end product. We have grid injection, fuel for transport, compressed biogas or bio-CNG, and liquefied biogas or bio-LNG. And then, of course, we can use the CO2 to create green hydrocarbons if we have any kind of process that need that. So if we, next slide. Here we have a grid injection. That's what we do mostly in Denmark. We inject the renewable natural gas or the upgraded biogas into the natural gas grid, so we don't have to pump up natural gas. And then it's very easily distributed, and there's a large capacity in the gas grid. Next slide, please. For some of the projects in Norway, they use what we call a closed loop system. So they have the garbage trucks come in with the garbage from the local municipality. Then they create biogas from that garbage, and then they fuel the garbage trucks and the municipality buses again. So it's a complete closed loop, and very nice solution really, where they use the gas that the municipality creates themselves. Next slide, please. And this is also actually a municipality plant in Norway where they bottle it and compress it. So these containers are filled with biomethane bottles, compressed gas, if you don't have a local gas grid. And of course, it can be liquefied. That means we have to remove down to 50 ppm of CO2, which is also possible. And then after that, it can be liquefied, which is more suitable for heavy transportation, such as larger trucks or ship. I think the other advantage from biogas is more preaching for the choir, so it has a lot of advantages. We remove all the waste and we get a good byproduct with this biomethane. Yes, you can take the next. And that's my presentation. Thank you very much.
Thank you, Alexander. Biogas Clean.
Yes, hello. My name is Torkild Dalgrim, and I'm founder and CEO of Biogas Clean. Next, please. We are specialized in the removal of hydrogen sulfide from biogas, meaning without any chemical consumption. We develop, we manufacture, and we supply fully automated gas cleaning systems and combining low operating cost with very high availability. We have approximately 275 plants in operation or under construction in 40 countries. And today we supply clean gas to approximately 600 megawatt of gas engines. And furthermore, we are removing the hydrogen sulfide from tail gas from close to 20 biomethane products, many of them in cooperation with ammonia gas. Compared to chemical H2S removal process, which is the common use in US, our operating costs are typically 10 to 20% only. The residue from our process is a sulfur-rich fertilizer, which can be recycled and applied on the field as a green fertilizer. We are able to design our system to any flow and the H2S content. What we see on a municipal wastewater treatment plant would be maybe a few thousand parts per million, but we have products on ethanol plants where we have up to 20 or 30,000 parts per million of hydrogen sulfide, meaning 2 or 3% per volume. And we reduce this down to gas engine quality, typically between 50 and 250 parts per million. Next, thank you. In the US, we have today 11 products in operation, and we have furthermore 3 projects under installation. We are working with a couple of US distributors. One of them is Clark Energy. The other one is Penn Power, which is strong on both the East Coast and the West Coast, and also Vatic Biogas, which is not part of Ovivo. Furthermore, we have a resident engineer in Wisconsin. Next, please. Most of our projects are removing the hydrogen sulfide upstream. The gas engines could be Jenbacher or could be manned from Nissen. We do not have we take the raw biogas, and no pre-treatment is necessary. In more than 2/3 of our products we use as liquid source and fertilizer source the treated wastewater. So the only operating cost is in fact a very minor power consumption. We have expressed the power consumption per cubic meter or per standard cubic feet of raw biogas. So you will see this is very, very low operating cost. Next, please. The combination of amine operating and our biological H2S removal system has some very big advantages. In the beginning in Denmark, where the biomethane or RNG production started back in 2014, today the winning technology is this combination. We have also products with water scrubbers, we have membranes, I believe even fuel PSA systems. But today, the vast majority of RNG products in Denmark are the combination of amine and the biological H2S removal system. The amine is able to treat the raw biogas, including H2S, so we can use our biological system in the tail gas without doing anything to the biomethane quality. It's the lowest combination that has the lowest methane slip and also the lowest electricity consumption. And the only major consumption is the heat, which it's possible to reuse in the biogas plants. Next, please. Our system is biological, and we use atmospheric air or pure oxygen, and there will be a formation of a biofilm, a bacterial process inside the tanks. So we have a system where we can fill the tanks with water and pressurized air and wash this packing media without any need to remove it outside from the tanks, as you might have seen in other technologies. Next, please. I will show a few examples. This is a product installed in 2013 in Minnesota, and you will see this the lower blue bottom. You will see that the flow is 2,300 square SCFM, and we have 2,500 ppm H2S in the raw gas, and clean it down to 200 ppm. Next, please. This is a product in Nevada and Reno. The flow is 900 SCFM, and the H2S in the raw gas is 1900 ppm. Next. This is a product again in Minnesota, back from 2016. The flow is close to 700 SCFM, and we have 3,500 ppm in the raw gas, taking it down to 100 ppm. Next, please. A small product also in Minnesota, supplied in 2017. Next, please. This is one of the first products we have made in cooperation with Biogas in Denmark. It's RNG. It's for grid injection. And what we have here is not the raw biogas flow, it's the flow of carbon dioxide. So we have here 350 SCFM, and because of the concentration of the hydrogen sulfide into the carbon dioxide flow, the H2S is rather high. It's 7,500 ppm. Next, please. This is a major product for nature energy in Denmark, and the production is close to 780 million square cubic feet a year. And in this product, the CO2 is utilized in the beverage industry. Next. Another product for grid injection in Denmark. Again, it's relatively high. You have close to 1,600 SCFM. Next. And then we have one of the latest installations in Denmark, again for nature energy. The flow of carbon dioxide is 1,270 SCFM. This product will have just started operation. Next. But as mentioned before, we have the vast majority of our installations is cleaning the H2S prior to the gas engines. And today, Jenbacher is not longer by Jenbacher or by General Electric, but INEO, but still the technology is the same. And I believe we have supplied at least 125 installations where we clean the gas prior to a gas or engines from Jenbacher. Thank you very much.
Thank you, Torkel. And I think we still have, even though a lot of the questions have been answered from the technology providers, there's still a few that needs to be answered. I think this one is to you, Torvald, Nissan Engines. Why choose an IC engine versus fuel cells?
In most cases, it's because of the high efficiency of the IC engines.
Okay. And what is to my own curiosity, how is the progress on the fuel cells doing? I haven't heard any on a wastewater plant yet. You know
No,
that?
I think yeah, I think it's because also the gas cleaning system has to be much more efficient than in front of a gas engine. So it also creates more cost for that system. And then again, the efficiency calculation gives the higher income of and utilization of the biogas.
Oh, okay, super. Then we got a question to Flemming Müller from Christine. Is the full-scale recovery facility in Vasilisborg? Oh, it just disappeared, that question. Okay.
Okay, sorry.
I think somebody answered it.
Okay, that was because I actually answered it online, so it disappeared. I didn't know.
That's super, Flemming. I'll just continue then.
But I can. Okay, continue.
Yeah,
Yes.
Yeah. You know, let's have it. There might be more than just Christine who's interested in the question.
Yeah,
so please answer it live.
Yeah, so the question was, did Aarhus Water design the Strobite plant themselves? And the answer is actually, well, no, we didn't. We did it together with Suez and another Danish technology provider, Stjernholm, which did all the installations. But we actually had the expertise hired at that time. He has since then left us for another position, but yes, we did it partly ourselves. That was it.
Super. Yes. Embroy, forgive my ignorance, but what if any are the difference? But what if any are the difference between Danish and U.S. natural gas pipeline standards? It will probably be for Amon gas, or since the standard varies across the country, California standards. Can you answer that question, Alexander?
Yeah, I've been trying to read a bit about it, and I don't think the difference is that big. For both standards, it's based on the CO2 content. In Denmark, it's actually based on the WOB index, but really it's the CO2 content that comes into play. And I can see that the requirement of maximum CO2 in California is more or less the same as in Denmark. Actually, it's a bit higher. And yeah, there's a bit of difference between how much oxygen are allowed and what the water content is allowed, but it's not a big difference.
So it's not something that sort of
it's not something that's problematic
in the way for the technology. No, okay, super. Yeah. And then we got one for Flemming from Greg. It's about if food waste. Wondering why it wasn't part of the Vasilisborg food waste co-digestion, and if siloxane are an issue in the biogas for which you must treat.
Well, the first question, why it isn't still part of it? Well, that was actually part of the legislation. So if we had to add food waste, we had to be a food a company that actually handled food waste, and that was why. So it's purely legislation. That's my understanding of it anyway. And the second question, what was that?
Siloxanes, are they an issue in the biogas for which you must treat? I think you do that. I'm pretty sure it does.
What I can't read it now.
Siloxane in the biogas. I think
Siloxanes.
you,
Oh, okay. Yes. We
yeah,
treat both
this,
for siloxanes and sulfur, definitely. But
yeah,
we don't have as high siloxane levels as in the US. I know that is something I've discussed with Torvald from Nissen before.
yeah. And the last one that we haven't answered yet is for Torvald again. Do most plants in Denmark install their CHP engines in buildings or prefab enclosures? And why is one preferred over the other?
Yeah, I can answer that. That it depends simply of building available for CHP installation or not. So in the most municipalities, if they have building available nearby the boilers and so on, they put them in the Indian room there. But if they have to build new buildings, then they prefer the prefab enclosures, as we have we have supplied to Hermitage and also to Viby and many other places in the world. So it simply depends if there is space in existing buildings and infrastructure for getting the heat distributed and so on, or electricity distributed, then they install it in a building. But if there is no space for that, it's much easier for them to have a prefabricated enclosure as a turnkey solution. For example, Viby was one where there was not space in the buildings, so therefore they decided to get this solution.
Super. And we got a question more for Dimitra and Ikogi. What is the recovery rate of the processing unit? In other words, what percentage of input is rejected, screened out of the system? I think you might have covered that earlier.
Yes, I have answered it, but of course it's depend of the incoming waste. And as an example, we can see here in Denmark, when we are dealing with household waste, it's what we call source separated organics. And there we have typically between 10 and 20% of inorganic material in the waste that we have to sort out. And
yeah,
but it's totally depending on the incoming waste.
Yeah, and then there's more questions for you. I got 2-3 more for you actually. Do you have plans for installation in the US and particularly in California? And what are the challenges, limitations?
No, unfortunately, we don't have any plants in California, but we hope to get it in the future. And the challenges is to find the right projects, the right partners, and the right investors.
Put some words on the right partners. Can you do that?
Yeah, for instance, if we are talking about you want to use food waste in a water treatment facility, then I think it's difficult to find a water treatment facility which will take the responsibility for that process. So you have to find another partner who can make the collection of the waste and be responsible for treating the waste so it's ready to put in the digester in a water treatment plant.
Okay.
Jens, this is Chris Voll. Could I chime in here quickly?
Yes, please. Yes, please.
Couple of quick comments. So to the question earlier from Greg about why isn't more food waste co-digested in wastewater plants in Denmark, I would also like to add that part of that is just market drivers. Right now, it is much more financially viable for that food waste to flow to centralized systems that manage both animal manure as well as food waste. So there's definitely a market driver there. And also just want to bring up, and Lars, I don't know if you want to put any more words to this, but Gemiden has done some research on delivering their biopulp to a wastewater treatment plant digester. And I know that there is some data and information available regarding that.
Yes, that's right, Chris. We have made some tests in Denmark, and as I understand it, there's no technical issue to mix the sludge and the biopulp.
And then just to add on to the last point, Lars is working closely with a number of entities, and per Greg's early comments at the beginning of the webinar, we do see the ECOG system as a great bridge between the waste management and wastewater sectors. And so Lars is working with some private waste companies, some public entities, and we do hope to find a good place for the first project here in the US sometime in 2021.
So, we got another question for Gemidan. Are odors generated with the system? If so, how do you manage odors?
We can put an odor removal system to our system so we can handle those issues. But in any cases, it's important to then store and treat the waste in a closed building. That's the only way you can control the odor. But if you do that, then have a good ventilation system, it's not a big issue to remove the odor.
A question for Renew. What are the opportunities for you in the US, and do you primarily work with Danish or local suppliers? And does it differentiate from state to state?
Well, it's a good question. We are, of course, we have some partners, Danish partners we are working with in let's say in some cases, but we are basically, we are not religious. We can work with anybody who can deliver a good, let's say, good equipment. But they also need to be competitive, and so far we have seen that European product seems to be competitive so far. But of course, a lot of equipment, pipes, etc., will be delivered from US. We basically today we are working in New York State, in New Jersey. We have a project just starting in Illinois, Chicago, and we don't see a lot of differences. There was a question about quality for gas to the pipeline, and as Alexander answered that question, we don't see a lot of differences. It's almost a zero tolerance for oxygen, very low tolerance for CO2. So yeah.
Yeah, and just to Paul, if I could, this is Chris Voll again, just to add,
Yeah.
Renew, really acts as the design and consulting agent for
Yeah.
a number of US-based developers, and then Danish solutions are fit into the projects as appropriate, and so I think there's a real role for Renew whether in the system here in the US. Thanks,
Chris. For us, I would say, to underline what I'm saying, is that for us, it's not only the capex, I mean the investment cost, but for sure also operation cost. So when we have been working and promoting also ammonia gas, it is because we're looking on the when you're talking about R&D, it's important that you can deliver almost 100% of the gas into the grid. If you're working with other technologies, you might need to look at maybe 95% recovery. So that is, we need to look on the efficiency and the overall cost. That is important.
We got a question for Novozymes. Do you have any full-scale installations using enzymes to increase biogas production and yields? Who should we contact for a quota? And do you provide performance improvement guarantees?
So right now we don't have any full-scale implementations here in the US, but we do have quite a few in Europe and looking to come over into the US and expand that presence. We also don't really do any guarantees due to the wide variety of variables that can come into play in any operational system or even just within the trials themselves. But we work really hard to mitigate any risks that might come up. And I mean, we work in a couple different ways with that, depending on the trial itself, depending on the operating parameters of the utility, based on basically all of those variables. So it's really, really site specific how that would be done. But I'd be happy to discuss this further. And I would be the contact for any quotes or further questions. And my email, I think, is put in the chat, and I think Sophie was going to send that out as well.
I think we will attach all contact information of all of you in our follow-up. Amon gas, what is the main differences between using amine upgrading instead of membranes? Can you answer that?
Yeah, sure. So membranes is a mechanical technology, which means it operates under relatively high pressure. It's compressed, the CO2 and the methane, and then it's forced through a membrane where it will be separated. So that means you have to compress the CO2 as well. And before you can do that, you need to remove other pollutants such as H2S and water. So the thing that we call gas conditioning actually happens before the upgrading process. Whereas amine just takes in the raw biogas directly from the gas storage or reactor tanks, and then do the upgrading first, and then all the gas conditioning afterwards. Which also leaves the H2S in the CO2 stream instead, which it's easier to handle in the CO2 stream because the majority of the technologies uses air to remove the H2S, which we really don't want in the biomethane. So if we can keep that on the CO2 line, we are most happy about that. So that's the main difference.
The final question for you is at what pressure are you able to compress the CO2?
Yes, and as mentioned, we don't actually compress the CO2 in the upgrading process, which means that the CO2 will leave the plant in atmospheric pressure. And if it's needed at any other applications, then it can be compressed and treated there to whichever pressure is desired.
That's super. I think we managed to answer all the questions.
Jens, sorry, this is Chris Full. I just saw another one come in that I think is important for Alexander to answer. It asked about the safety concerns around amine, and I think there's some misconceptions out there. So I think it's a kind of an important one for.
Yes, it is. I didn't see it, Chris.
Yep.
Correct.
Sure.
So, and you got the question, Alexander.
Yes. So amine is, in general, an organic solvent, and it's mixed with water in this case. So it's a closed loop system, and it runs internally in the columns you saw before. It runs completely internally in them, and there's not really any consumption. So there's no release of the amine into the sewage or whatever. In Denmark, the amine we use here is used to wash beets, sugar beets. So we use it in food process. And in general, the typical amine that we use is used in household products such as cleaning products or makeup or shampoo. So it's not what you would consider a toxic thing to handle. Of course, It is an alkaline, so it's not good to get directly on the skin, but neither is concentrated soap. So yeah, I would say the same safety concern as that.
I think that answered the question good. So thank you, all of you. And yeah, reach out to us if you need anything additional from the contents in the webinar today, or also if you just want to have a visit from us and a talk to us with some experience out of the wastewater operation, and also the biogas folks, Chris and Cecilia, out of Denmark. So yeah, and I think actually we should go to the deep dive with the technology providers. So if there's anybody, Sophie, can you open the mics if there's anybody who raises their hand, and then they can talk directly to the technology providers.
I guess we ought to, Jens, we ought to just say thank you to all the presenters and everybody attending. In case folks have to leave after the kind of formal part of the program. We did have some good Q&A, but we are willing to stay on for a bit more, as are the technology providers, but only if people have questions. So, but in the meantime, I just want to put that thank you out there, and thanks to Jens for doing a great job moderating.